We are done with finding out the area of boom, or to say the skin stranger model from a actual beam cross section, and we have also seen how to do bending analysis of a skin stranger model. That is, how to find out the direct stresses at the booms due to an applied bending moment. Now the next thing that we need to understand and analyze is how to find out the shear stress or shear flow in a skin stranger idealized beam. So on the right hand side you see a skin, so this is a skin stranger idealized beam. Okay, and I have also drawn the coordinate system, Z being the lengthwise direction of the beam. Okay, so we have the skin stranger idealized beam with several booms, and the skin between the booms which are assumed to have a negligible thickness or a zero thickness. And as I have said earlier, I'm also going to repeat, the booms are going to take the direct stress developing due to the applied moment, and the skin is going to take the shear stress, which could be either because of the shear force applied or because of the torsion. So in this lecture we will talk about how to find out the shear stress, or to say the shear flow in the skin due to an applied shear stress, shear force, Sy and Sx. Now what I have done is that I have highlighted a portion of the skin stranger idealized beam, and I have drawn the enlarged view. So where B1 and B2 are the two booms. Now if I take boom 1, so let me call this as boom 1, and try to find out the stresses in boom 1. Okay, what are going to be the stresses? So since the boom are going to take the direct stresses, okay, so what is being applied? Sorry, I missed that. So the beam, so this beam is under an applied shear force, Sx and Sy. Okay, so now if I consider this boom 1, let me see what are the stresses acting on this boom 1. So I have separated out, the boom, and these two parts are the skin adjoining to boom 1. So this is the skin adjoining or adjacent to the to boom 1, and this is also the skin. Okay, now let us see what are the stresses on boom 1. So 1 is going to be the direct stress. Because shear force is acting, it will produce a moment, and that moment is going to produce direct stress on the boom. So let me call this as sigma z, and therefore this is going to be sigma z plus del sigma z by del z into dz. Right? So what are the other stresses? So the skin is going to experience the shear stress and the corresponding shear flow. So the shear stress here, let me call this as Q1, shear flow. Okay, if this is Q1, then the complementary shear force on the other two direction is going to be Q2, and this is going to be Q2. So since Q1 is acting on the skin, and equal and opposite Q1 is going to act on the side of the boom. So similarly, I will have Q2 here. Okay, if this is Q2, then on the skin I have Q2, and I have a complementary shear flow Q2, and this is Q2. Okay, so these are the stresses that are going to act on this boom and skin assembly. Now let me do force equilibrium in z direction. For the boom. So what are the stresses in z direction? I have sigma z plus del sigma z by del z into dz, okay, into the area, which is boom 1, minus sigma z into b1. That is the direct stress part, and then I am going to have Q2. Q2 is the shear flow, so that is shear stress into thickness. So I have to just, to get force, I have to just multiply this by dz. Okay, this is in the positive z direction, and then I have Q1 into dz, that is in the negative z direction, and this is equal to 0 because for equilibrium. Now if I simplify this, so if I simplify this equation is going to lead to del sigma z Okay, so this is the simplified version of the force equilibrium equation. Let me call this as equation 1. Now, let me express sigma z in terms of the moment applied. Okay, so I know the expression of sigma z. So if I try to write sigma z in terms of the moment applied, so sigma z is going to be my, if you remember this, right, we have derived it for bidirectional bending, my into ixx minus mx I hope I have written this correctly. Okay, so now therefore, so let me call this as equation 2. So from equation 1 and equation 2, what do we get? We get q2 minus q1. We get q2 minus q1 is minus del sigma z by del z into b1. So that in turn is going to be minus okay. So now this can further be written as, we know that del M by del Z is actually the shear force. So del My by del Z is Sx. We have done this before, right? So this is nothing new. So Ixx minus del Y by Ixy. Okay, so I have done it for only one, and one is the arbitrary here, right? I have just named the boom as B1. It could be anything. Okay, so I can actually generalize this equation and write this as, I could actually generalize this and write this equation as QR minus QR minus 1, where R is the number of, no, is the index for the boom, is this whole thing into BR XR minus this whole thing into BR YR. Okay, so this equation is going to give me the expression for shear flow in a skin stringer idealized cross section. Okay, now let us understand how much advantage or how much easy calculation this is going to give us. Okay, if you remember the shear flow in a non-idealized cross section, okay, or in a cross section that was not simplified using skin stringer idealization, this was actually this term, which is just a product here, were actually an integral function. It was x ds and this was y ds. Okay, and as you have probably, and this q2 was a function of s. Okay, and as you will be able to appreciate that finding out this integral was really a very cumbersome process, and it made the calculation of shear flow in an actual cross section it was very tedious. Okay, So, but as we idealize or simplify it with this boom and skin model or skin stringer model, then our integral get abolished and it is just replaced by a product. Okay, and therefore your shear flow is no longer a function of S. Probably you will be able to appreciate that for a skin stringer idealized cross section, okay, Q is constant in a skin between two booms. Okay, so if I go back to my model, so this part is going to have, I will use a different color. So this part is going to have a single Q, which I can call Q12, which is not a function of S. Okay, unlike my actual cross section, similarly, I mean this part, so if I call this as if I call this as zero point 0.3, then this part is going to be Q23, which is not a function of S. Okay, but if you look into the actual cross section, if this was the actual cross section, then this would have Q, which would be a function of S. Okay, and that brought in a lot of complexity in the analysis, a lot of tedious calculation in the analysis, which we can simplify or get rid of and uh, get a much easier calculation process if we idealize or approximate it using a skin stringer model. Okay, now with this, let me solve an example which will perhaps give us a better understanding of the problem. Okay, so let me just clear the canvas and so this is, so suppose I have a skin stringer idealized C section. Okay, so let me give the dimensions. So the dimensions are, so all dimensions are in millimeters. So this is 200 millimeter. This is 200 millimeter. This is also 200 millimeter. It is symmetrical cross section. And area of the booms, area of each boom is 300 millimeter square. Okay, let me number the booms. So this is 1, this is 2, this is 3, this is 4. So the question asks for find the shear flow and the shear center for Sy equals to 4.8 kilonewton passing through the shear center. Okay, so I have a shear force which is Sy, which is equal to 4.8 kilonewton, and it is passing through the shear center. So this is the shear center, and I have to find out the position of the shear center, which let us assume that it is zeta from the outer web. Okay, and now I have to solve this problem. So let me write down the expression for shear flow. Okay, so I know that QR minus QR minus 1 is going to be minus okay. So out of this, since the cross section is symmetric, Ixy is equal to 0 and there is no shear force applied in x direction. So Sx is equal to 0. So I can actually get rid of this. Okay, so my things get much more simplified. So QR minus QR minus 1 is just going to be minus Sy by Ixx into BR into YR. So this is the equation that I have to deal with. Okay, so let me find out let me find out Ixx. So for a skin stringer idealized case, Ixx is going to be very simple. So that is going to be uh, very simple, and it is going to be 4 into 300 meters square into 200 whole square, right? And that into millimeter 4. So this into this millimeter 4. So if I calculate this, this turns out to be 48 into 10 to the power 6 millimeter 4. Okay, so this is my Ixx. So I know Sy, I know Ixx. Now I need to find out the shear flow. So let me start with for flange for flange 1 2. Okay, so now let us look for flange 1 2. Okay, so Q12, okay, so minus Q0, Q0 is going to be 0 because we are starting from the free end. So Q12 is going to be minus Sy by Ixx into B1 into Y1. So that is going to be minus 4.8 into 10 to the power 3 Newton by 48 into 10 to the power 6. B1 is 300 and Y1 is plus 200. Okay, so this turns out to be minus 6 Newton per millimeter. Okay, now let us see for web 2, 3. Okay, so is this going with the number? Yes. So for web 2, 3, for web 2, 3, it is going to be Q23 minus Q12 is going to be minus Sy by Ixx into B2 into Y2. So therefore Q23 is going to be minus 4.8 into 10 to the power 3 into 300 into 200 and minus 6. Okay, this is equal to Q12, right? So this is going to come as minus 12 Newton per millimeter. Okay, now let us find for flange 3, 4. So if I try to find out for flange 3, 4, it is going to be Q34 minus Q23 is going to be minus 4.8 into area of the boom 3, that is 300, into Y3, that is minus 200, and minus 12. This is equal to your Q23. So this is going to be minus 6 Newton per millimeter. Okay, so I have got the shear flow for all the legs or portion of the cross section. Now let me try to draw the shear flow. So if I draw the shear flow, this is going to look something like this. So let me first draw the section. Okay, so this is 1. This is 1. This is 2. This is 3. This is 4. Now let me see. For flange 1, 2, I have got, so Q12 is minus 6 Newton per millimeter. Q23 is minus 12 Newton per millimeter. Okay, and Q34 is minus 6 Newton per millimeter. So if I draw them, it is minus, so S was in this direction, I was moving from 1 to 2. So this was my S. Okay. So my shear flow is going to be 6 Newton. This is 6 Newton per millimeter. This is going to be 12 Newton per millimeter. And then I have 6 Newton per millimeter. Okay, so that is done. Right, now I have to find out the shear center. So how am I going to find out the shear center? Okay, so let me assume that the shear force Sy, as I have done before, Sy is acting at a distance zeta from the outer wave. Okay, so if I find out moment about point, let me find out the moment about point 2. So taking moment about point 2, so it is going to be Sy into zeta, and that is Q34, right? So that is going to be 6 into 200. Okay, so that is going to be 6 into 200 into the length of the, sorry, 6 into 200 is the force, this is the force, into 400 is the momentum. Okay, and therefore I have 4.8 into 10 to the power 3 zeta is going to be 6 into 8 into 10 to the power 4. So if I solve this, I should get zeta as 100 millimeter. Okay, which is going to give me the location of shear center. Okay, so this problem is done. So one thing I want you all to note is that the main difference between finding out the shear force for the actual cross section and that for this skin stringer idealized cross section. So for actual cross section, the shear distribution would have been certain function, right? We have already done this problem before. So if you remember correctly, so the shear force for a C-section was something of a parabolic shape, which was something like this, if I remember correctly. Okay, and something like this. Okay, so this was always a function of, the shear flow was always a function of S, and since it was a function of S, finding out the shear center or working with the shear flow was indeed much more difficult than that for a skin stringer idealized configuration, where the shear flow in each of the portion of the cross section between two booms is constant. So let me write down, for a skin stringer idealized section, shear flow is constant between any two stringers. any two booms, sorry, right? So with this, we will end this lecture. In the next lecture, we will talk about certain corollaries for finding out the shear flow in a skin stranger idealized beam, and also solve an example of a closed skin stranger idealized cross section. Thank you.